Hi all, this video is for chapter 3, section 2, called conditional probability and the multiplication rule. So let's first discuss what we mean by conditional probability, and then we'll extend this to the concept of the multiplication rule. So we want to learn how to find the probability of an event given another event had occurred, which is a conditional probability. We want to learn how to distinguish between events that are independent from those that are dependent, and then finally how to use the multiplication rule, find the probability of events occurring in sequence. First step, conditional probability. The conditional probability is the probability of an event occurring given that another event has already occurred. So given that we already know something happened, what's the probability of another thing happening? The notation we use here is P parentheses big B or event B with a slash, vertical slash, which is interpreted as such that or given A, and read the probability of B given A, or the probability of B happening such that A has already happened. For an example, let's select two cards in sequence. Find the probability of the second card is a queen, given the first card is a king. Assume that the king is not replaced. This has a lot to do with replacement. And if it's not stated, we're to assume that there was not replacement. If we are to assume that there was replacement, it's got to be said that there was replacement. So if it's not stated, just assume there was no replacement. So we just want to know the probability the second card is a queen, given the first card is a king. Well, the probability that the second card is a queen, given that the first card is a king, is the number of ways we could satisfy the event of being a queen divided by the total number of ways that anything can happen. But we already removed a king from the deck of cards. There are 52 cards in the deck, but we already got rid of one of them, which is a king. So there's only 51 left. So we see here the probability the second card is a queen given the first is a king is 4 out of 51. How about more of a data-driven example? Here's a survey of 2,276 social media users asked whether they have ever been offended by something they saw on social media. Find the probability that a user is male given the user was offended by something on social media. So given that they were offended means that they said yes, and therefore I'm only going to be looking at this subset of the data. Because it said given they were offended, so they must have said yes, so I must look only at here. Now we're going to find the probability they're male given they're in this column of data. The probability that they're male would be 532 out of the total number who had said yes, because it said given they have been offended. So you get, if you run the calculation, 0.462 or just over 46%. So it's interesting in a question like this is we could start to ask a question, is being offended on social media dependent on if you are a male or if you are a female? You could rephrase that question by saying, is the percentage of males significantly different than the percentage of females who are offended? So that's the idea of things being dependent or independent. Two events are independent if the occurrence of one does not affect the probability or the occurrence of the other event. So they're independent. They do not depend on each other if one event occurring does not affect the probability of the other event occurring. We could say mathematically the probability of B given A is equal to the probability of B because they're independent. Knowing A happened did not change anything. You didn't have to tell me that A happened because B is not dependent on it. Or in the other order, the probability of A given that B had happened is simply just the probability of A. We'll show you some examples. If they're not independent, then they are dependent, meaning the probability of B given A is not just going to be the probability of B. Knowing that A occurred changes the game. Let's decide whether these are independent or dependent. We're going to select a king from a standard deck of 52 playing cards, not replacing it, and then selecting a queen. Well, selecting a queen second is going to depend on what happened first. The probability of B given A, the probability that the second card is a queen given the first card is a king, is 4 out of 51. But the probability of just selecting a queen without the given A part is 4 out of 52. So notice these are different. These are not the same, and therefore they are dependent. The second card depended on the first. The occurrence of A changed the probability of the occurrence of B. What about this example? We're going to toss a coin and we want to get ahead. That's the event A. And then we want to roll a 6-sided die and obtain a 6. Well, the die doesn't care what you just did with a coin. So the probability of rolling a 6 given you flipped ahead on a coin is still 1 out of 6. Rolling the die was unaffected by what happened with flipping of the coin. So the probability of B given A here is simply just the probability of B. You didn't need to tell me about the head being flipped on the coin. So these would be independent events. It's not always super straightforward. This, let's go back to this slide here. These statements here are very easy to show for theoretic probabilities for flipping of coins and cards and whatnot. It's not super great for statistical probabilities because the probability of B given A and the probability of B in context, we can go back to this situation. So if we know you had said yes, that you've been offended, the males have a probability of 532 out of 1,151, or about a 46% chance. If I calculated the same for females, is it going to be radically different? If it's similar to 0.462, then being a male doesn't seem to depend very much on how you feel about social media. My point is that this is straightforward for theoretical events, theoretical probabilities. For statistical probabilities, we should use more of a squiggly equals or approximately. Things are independent if the probability of B given A is roughly the same as the probability of B. So we have to take it with a little grain of salt. Okay, and then we were here, but how about this? Is driving over 85 miles per hour, event A, and then getting in a car accident B dependent or independent? Well, over 85 miles an hour is pretty darn quick. You start driving that fast and you're probably more likely to get into a car accident. So we would call them dependent. Driving over 85 miles per hour increases the chance of getting in an accident. I'd also like to point out, this is pretty fast, unsafely fast. On a highway, you could go unsafely slow. I've seen slow drivers causing a lot more problems than the mildly fast ones, but this is a little too fast. So here's how the conditional business and dependent independent comes to play. In the so-called the multiplication rule, the probability that two events A and B will occur in sequence is given by probability of A and B is the probability of A, because this is the first thing that happened. This can't be dependent on anything else because nothing happened prior that we care about. And then we're going to multiply it by the probability the second thing happens, B, given A happened. We have to keep in mind that A had already happened. If A and B are independent, remember the probability of B given A will simply be the probability of B. So if A and B are independent, the multiplication rule just says, just multiply both of their individual probabilities. I wouldn't really commit this to memory. This one is the one that you should really commit to memory because it gives you the caveat. Possibly the first thing that happens affects the second thing to happen. Now, these can be extended for any number of independent events. This one certainly can be extended. This one can be extended to, say, and C, and we'd have to multiply by the probability that C happens given that A and B happened. So we could look at 3 cards. What's the probability you get a king, then a king, then a king? you would say, well, the probability the first one is a king is 4 out of 52. And then the probability the next is a king is 3 out of 51 because there's only 3 kings left out of the 51 remaining cards. And then we'd multiply by 2 out of 50 because there are only 2 kings left out of the remaining 50. So this one can be extended. We just have to keep in mind the conditionality, the possible dependence of later events on previous events. 2 cards are selected without replacement. What's the probability you select a king and then select a queen? So the probability of a king and queen, and the order is important, is that we get the king first, and then we multiply by the probability of getting a queen, then a king. Okay? The probability we get a king is 4 out of 52. The deck was shuffled and fresh here. The probability we now get a queen, given we drew a king already, is 4 out of 51. So we multiply fractions by multiplying tops, multiplying bottoms, and getting 16 out of 2652, or a 0.006 shot. I want to caution you here. This is not the probability of selecting 2 cards and having a king and a queen. This is more picky. This is selecting 2 cards and the first is a king and the second is a queen. If we wanted to answer the more general question of selecting 2 cards and seeing a king and a queen, we would have to calculate this one that we just did, and then we'd also have to realize about we could have gotten a queen and then a king, which would carry the same probability. You could double check that. And the next section will realize that that's an or situation. You get a king, then a queen, or a queen, then a king. And we're going to realize in that chapter, in that section, that we're going to add them. So kind of in a nutshell, and is multiplication. And refers to multiplication, or is going to refer to addition. A coin is tossed and a die is rolled. Find the probability that you toss a head and then roll a 6. Well, they're independent events. Literally, you could write the probability of 6 given you flip a head, but that will still just be 1 out of 6. So the probability the first thing happens, we flip the coin in his head, is 1/2. Then we roll the die. The probability you get a 6 given you flipped heads is 1 out of 6. Multiply together, you get 1 out of 12, or a 0.083 shot. For anterior cruciate ligament, or ACL reconstructive surgery, the probability that is successful is 95%. Find the probability 3 ACL surgeries are successful. Okay, 95%. The chance for surgery, they're going to be independent, essentially. This 95%, we imagine, comes from a massive amount of data. It's not 95 out of 100. Because if you get 1 success, then the next is going to be, 94 out of 99. We've imagined the 95% came from a massive, infinite, actually, set. So the first surgery must be successful, 95%. The second surgery being successful is independent of the first surgery being successful, as well as the third. So we just multiply 0.95 together 3 times, and the probability 3 ACL surgeries are successful is about 85.7%. What's the probability that none of them are successful? Well, that means the first one can't be successful, the second one cannot be successful, and the third cannot be successful. Now, maybe you're thinking, is this the complement of them all being successful? No. The complement of them all being successful, which we just found here, is not all successful. And not all successful means you have at least 1 failure. So, the first could have been a failure, or the second, or the third. Or it could mean 2 failures, or all 3 failures. So keep in mind, the complement of all is not none. The complement of all is not all. So we want to find the probability that none are successful. It's not the complement of them all being successful. So we just have to think, well, the first one can't be successful. The success rate is 95%, so 5% is not successful. So we must have not successful, and then not successful, and multiply. So we get a very unlikely chance, 1 out of 10, 1 out of 100, 1 out of 1,000, 1 out of a 10,000 shot. So if these 3 surgeries are performed 10,000 times, only about one of them are you ever going to find all three of them to have been a failure. What's the probability at least one is successful? All right, this is, take note, this is when the complement is super helpful. When you see in the event statement an inequality like this, at least, or others like at most, or less than, or more than, think about the complement. So this event is at least one of the three is successful. The complement of that is not at least one of the three is successful. It's a strange way of speaking, but what does this mean? Not at least one of the three are successful. Was at least one of the three successful? Nope. That means none of them were successful. So this statement is actually the complement of none are successful. It takes a little bit of, a pause when you put the word not here. Not at least one of the three is successful. Not at least one of the three is successful, meaning none are successful. So that's the complement. The complement of at least one is successful is that none are successful. And the relationship between the probability of an event and its complement is the probability of an event is 1 minus the probability of its complement. We already calculated this in the last slide. None are successful carried this 1 out of 10,000 shot. So the probability that at least one of the three is successful is 0.9999, 99.99% chance. Almost a certainty, but not. Super likely though. All right, this is a long one. We have 18,187 U.S. allopathic medical school seniors applied to residency programs and submitted their residency program choices. Of these seniors, 17,057 were matched with residency positions. Okay, so the probability they were matched with a residency position is this 17,000 and change divided by this 18,000 and change, with about 79.2% getting one of their top three choices. So 79.2% of these 17,000 got one of their top three choices. That's pretty good. Medical students rank the residency programs in the order of their preference, and program directors in the United States rank the students. The term matched refers to the process whereby a student's preference list and a program's director's preference list overlap, resulting in the placement of a student in a residency position. Well, that's really wordy. What do they want to know? Find the probability that a randomly selected senior was matched with a residency position and it was one of their top three choices. Okay, we want to find the probability they were matched with a position and it was in their top three. Let's go back for a second. These many were matched. Okay, so the probability they were matched is this divided by this. And they want to know, and they got one of their top three choices. So then we'll have to have the probability they got one of their top three choices given they were matched. This number is already, this probability is already the probability that they got their top three given they were matched. So this problem, as long as it was to read, is actually really quick to do. The probability of A and B, and where A is being matched to a residency position and B is being matched to one of the top three choices, the probability of A and B is given by the probability of A times the probability of B given A. But the probability of B given A is the probability they were matched to one of their top three choices given that they were matched to a residency position. We were given this piece of information already. That's what that 0.792 was. So you smash this into the calculator and you should get a 0.743. That's a pretty good probability. That's almost a 3 out of 4 shot. So pretty likely. What's the probability a randomly selected senior that was matched to a residency position did not get matched with one of their top three choices? Well, we need to use the complement. They were matched, but they didn't get in the top three. Well, we know that 79.2% did get in their top three. So the complement of that, or a little over 20%, did not get matched with one of their top three. So another example of using the complement. Would it be unusual for a randomly selected senior to be matched with a residency position and it be one of the top three choices? Well, no, we just found out that the answer to the probability was a healthy 0.743 shot. They say that's greater than 5%. Something, 5%, just to make note, 5% is a pretty good guideline and we'll use to determine when something is unusual. If its probability is less than 5%, we call it unusual. So anything greater than 5%, we don't typically call unusual. Very unusual, we'll use as 1%. If it's a less than 1% probability, it's very unusual. So less than 5%, unusual. Less than 1%, very unusual. But greater than 5%, not unusual. 74.3% is well over 5%. So it's not unusual at all. As a matter of fact, it's quite likely to happen. Okay, that's section 3.2. You can work with some problems from the book, try some Blackboard quizzes, and when you feel comfortable, try the quizzes on MyLab. If you have any questions, please reach out to me. Take care.